Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from definite integrals involving greatest integer function and inverse trigonometric function, right? So here we have to solve this integral which is from minus pi by 3 to 0, and here we have the greatest integer of cot inverse 2 divided by 2 cos x minus 1 plus cot inverse cos x minus half, right? So here this bracket indicates the greatest integer function, right? So this is a very easy problem, but from appearance this problem seems to be a difficult one, right? But here if we apply some concepts from greatest integer function and the properties of inverse trigonometric functions, we can arrive at the result very easily and very quickly, right? So let us see how we can solve this integral. So now let us write this integral as I, right? So now I can be written as integral from minus pi by 3 to 0, and here we have the greatest integer symbol, and this is cot inverse, and here we have 2 divided by 2 cos x minus 1, and here we have cot inverse, and cos x minus half can be written as 2 cos x minus 1 divided by 2, right? So the first important thing here is to note that here we have cot inverse, and inside the brackets we have 2 divided by 2 cos x minus 1, right? Here also we have cot inverse, and here the term which is inside the brackets is the reciprocal of this term, right? So 2 divided by 2 cos x minus 1, and here we have the reciprocal of this term, that is 2 cos x minus 1 over 2, right? So before proceeding further, let us quickly take up some concepts from inverse trigonometric functions to simplify this integral. So now let us first take up the coordinate system. So here we have x-axis, here we have y-axis, and here we have the four quadrants, right? So here we have the first quadrant. This is first, this is second, this is third, and this is fourth, right? And here we see that the limits vary from minus pi by 3 to 0, right? So this indicates that we are in the fourth quadrant, right? See here we have a negative of pi by 3, right? So whenever we measure the angle in clockwise direction, we take it as negative, right? So here we have, suppose this angle is minus pi by 3, so we have to integrate this function from minus pi by 3 to 0, right? So when we go from minus pi by 3 to 0, it implies that we are residing in the fourth quadrant. So here x varies from minus pi by 3 to 0, right? So it implies that we are in the fourth quadrant, right? And from the sign convention of trigonometric functions, we know that in the first quadrant, all the trigonometric functions are positive, right? And in the second quadrant, the sine function is positive, right? And the other trigonometric functions are negative. And in the third quadrant, the tan function is positive, and the other trigonometric functions are negative. Obviously here cot function is also positive, and here cosec function is also positive, because cosec function is inverse of sine, that is reciprocal of sine, and here the cot function is equal to 1 over tan function, right? So here in the first quadrant all the trigonometric functions are positive. In the second quadrant, sine and cosec are positive. In the third quadrant, the tan and cot function are positive, and in the fourth quadrant, the cosine function and the sec function are positive, right? So this is the sign convention for trigonometric functions in the fourth or in the four quadrants. So now here we have the cosine function, right? And we are in the fourth quadrant. So it implies that the cos function is positive in the fourth quadrant. It means when x belongs to minus pi by 3 to 0, right? So cos x is greater than 0 for all x belonging to the fourth quadrant, right? So 2 times of cos x is obviously greater than 0, and we can now write 2 cos x minus 1 is also greater than 0, or it is positive in the fourth quadrant, right? So obviously 2 cos x minus 1 divided by 2 is also greater than 0, or it is positive, right? So now this quantity is positive, and also this quantity is positive, because when 2 cos x minus 1 divided by 2 is greater than 0, obviously 2 divided by 2 cos x minus 1 is greater than 0 when x belongs to minus pi by 3 to 0, right? So this is an important concept in this problem. And now we will see an important property of inverse trigonometric function. So now let us take this quantity, that is 2 cos x minus 1 over 2, as say theta, right? So let us consider 2 cos x minus 1 over 2 as theta. Then this term, which is inside the symbol of greatest integer function, is cot inverse, and here we have 1 over theta, and here we have cot inverse theta, right? So now the from the properties of inverse trigonometric functions, we know that cot inverse of theta is equal to tan inverse of 1 over theta, right? For theta greater than 0, right? And here we have assumed that 2 cos x minus 1 over 2 is theta, and this quantity is greater than 0. So obviously theta is greater than 0, so this property holds, right? So cot inverse theta is equal to tan inverse 1 over theta. So now we can replace this cot inverse theta by tan inverse 1 over theta, right? So now this expression, that is cot inverse 1 over theta plus cot inverse theta, can be written as cot inverse 1 over theta plus uh, tan inverse 1 over theta, right? So we have replaced cot inverse theta by tan inverse 1 over theta. And here again, we'll make use of one important property of trigonometric functions, that is tan inverse theta plus cot inverse theta is equal to pi by 2 when theta belongs to the set of real numbers. So here cot inverse 1 over theta plus tan inverse 1 over theta is equal to pi by 2 by virtue of this property, right? So when theta belongs to r, then 1 over theta also belongs to r, right? So now this term which is inside the brackets is now equal to pi by 2, right? So now this integral I can be written as integral from pi by 3 to 0, and here inside the greatest integer function symbol we have pi by 2, right? Because cot inverse 2 over 2 cos x minus 1 plus cot inverse 2 cos x minus 1 over 2 is equal to pi by 2, right? And we know that the approximate value of pi is 3.14, and when we calculate pi by 2, it is approximately equal to 1.57, right? So here the greatest integer of pi by 2 is equal to greatest integer of 1.57, that is equal to 1, right? So now this integral reduces to minus pi by 3 to 0, and here for greatest integer of pi by 2 we have 1, right? So here we have dx also, so here we have dx, right? And now the integral of dx is simply x. So now I is equal to x, and the limits of integration are from minus pi by 3 to 0, and we can now substitute the limits and we'll take the difference. So we have 0 minus, and here we have minus pi by 3, and that is equal to 0 plus pi by 3, that is equal to pi by 3, right? So the value of this integral is equal to pi over 3, right? So viewers, we have seen here the important properties of inverse trigonometric functions and how to evaluate these type of integrals.